We're going to talk about shortest paths. And we're going to talk about shortest paths for 3 lectures. So this is a trilogy. Today will be shortest paths 1. I've been watching far too many versions of Star Wars this weekend. I saw the musical yesterday, matinee. That was fun. MIT musical. That was fun. Of all 3 plays, all 3 movies in about 4 hours. That was a bit long. And then I saw the one-man show on Friday. And one-man Star Wars, the original 3 movies in 1 hour. That was the opposite of too long. Both were fun. So now I get my trilogy fix. All episodes. This is first. We're going to start with A New Hope, and we're going to talk about the shortest paths problem and solve one particular version of it, a very interesting version. And then we're going to look at increasingly more general versions as we go on. Shortest paths are sort of an application of dynamic programming, which we saw last week, and greedy algorithms, which we also saw last week. So we're going to build that and get some really interesting algorithms for an important problem, which is how to get from Alderaan to, I don't know, Cambridge in as quickly as possible, okay, when you live in a graph. So there's geometric shortest paths, which is a little bit harder. Here we're just going to look at shortest paths in graphs. Now, hopefully you all know what a path in a graph is, but some very quick review in particular because we're going to be looking at weighted graphs. So the usual setup, suppose we have a directed graph, G, has some vertices, some edges. We have edge weights, make it a little bit more interesting. So this is just a real number on each edge. So edge weights are usually given by a function. W. For every edge, you get a real number. And then if we look at a path in this graph, so we're going to use some simple notation for paths called a path P. Starts at some vertex, then goes to some other vertex, and so on. Let's say the last vertex is VK, and each of these should be a directed edge in the digraph. Okay, so this is a directed path, has to respect edges in here. And we'll say that the weight of such a path is just the sum of the weights of the edges along the path. And we'll call that W of P. So sum I equals 1 to k minus 1 of W V I plus 1. Okay, so just to rub it in, and in particular how general this can be, we have some path, it starts at some vertex, there's some edge weights along the way. This is some arbitrary path in the graph, in some hypothetical graph. Okay, this is mainly to point out that some of the edge weights could be negative, some of them could be 0. The sum here is minus 2. So the weight of this path is minus 2. And presumably the graph is much bigger than this. There's just one path in the graph. We're usually thinking about simple paths. They can't repeat a vertex, but sometimes we allow that. Okay, and then what we care about is the shortest path, or a shortest path. Again, this may not be unique, but we'll still usually call it the shortest path. So we want the shortest path from some A to some B, or we'll call that vertices U and V. And we want this to be some path of minimum possible weight, subject to starting at U and going to V. Okay, so that's what we're looking for. In general, give you a vertex U, give you a vertex V, find a shortest path as quickly as possible. What's a good algorithm for that? That's the topic for the next 3 lectures. We will usually think about a slightly simpler problem, which is just computing the weight of that path, which is essentially computing the distance from A to B. So we'll call this the shortest path weight from U to V. And we'll denote it by delta of UV, little delta. So this, it's the weight of the shortest path, or weight of every shortest path, or in other words, it's the min over the weight of each path from from U to V. So P here's a path. Okay, so you just take you consider exponential. There could be a lot of different paths. There could, in principle, be infinitely many if you're allowed to repeat vertices. You look at all those paths, hypothetically, you take the minimum weight. Question?
But if you're allowed to have negative edge weights, then doesn't that mean that there may be no minimum weight?
Good. Okay, my next question was going to be, when do shortest paths not exist? And you've hit upon one version, which is when you have negative edge weights. So in principle, when you have negative edge weights, some shortest paths may not exist, in the sense that there is no shortest paths. There are no shortest paths. There is no shortest path from U to V. Okay, in particular, if I have 2 vertices U and V, and I want the shortest path between them, and I have negative edge weights, well, this is fine. I can still compute the weight of a path that has negative weights, but when specifically won't I have a single shortest path from U to V? So go ahead.
If you can find a cycle that's negative weight.
Good. So if I can find a cycle somewhere along here whose total weight, I'll say the sum of all the weights of these edges is negative, then as long I get there, I go around as many times as I want. I keep decreasing the weight because the weight is negative. I decrease it by some fixed amount, and then I can go to V. So as long as there's a negative weight cycle reachable from U that can also reach V, then there's no shortest path. Because if I take any particular path, I can make it shorter by going around a couple more times. So in some sense, this is not really a minimum. It's more like an infimum for those who like to get fancy about such things. But we'll just say that delta of UV is minus infinity in this case. There's a negative weight cycle from U to V. So that's one case we have to worry about in some sense. But as long as there are no negative weight cycles, delta of UV will be something bigger than minus infinity, some finite, bounded below by some finite value. Even if you could have negative weights but still no negative weight cycle. For example, there might not be any cycles in your graph. But that's still interesting. And I guess it's useful to know that you can get from A to B in negative infinite time. It's great. It's time travel. Okay, if the weights happen to correspond to time. But when else might shortest paths not exist? So this is one case, but there's another. A simpler case. It's not connected. There might not be any path from U to V. This set might be empty. There may be no path from U to V. Here we have to define what happens. Here we'll say it's infinity if there's no path from U to V. So there are these exceptional cases, plus infinity and minus infinity, which are pretty intuitive, because it takes a really long time to get from U to V if there's no path there. You can't get there from here. Okay, but that's the definition. Most of the time, this is the case we care about, of course. Usually, this is a finite set. Okay. Good, so that's the definition. Now let me tell you, we're going to get a few basic structural properties about shortest paths that will allow us to obtain good algorithms for finding these paths when they exist. And in particular, we want to use ideas from dynamic programming. So if I want to use dynamic programming to solve shortest paths, what do I need to establish? What's like the first thing I should check? You've all implemented dynamic programming by now, so it should make complete sense. Hopefully. At least more sense than it did a couple of weeks ago last week when we learned it. Dynamic programming is something that grows on you. Every year, I think I understand it better than the previous year. But in particular, when you learn dynamic programming in this class, there's this nice key property you should check. Yeah?
Optimal substructure.
Optimal substructure, good. This is the phrase you should keep in mind. It's not really enough for dynamic programming to be useful in an efficient way, but it at least tells you that you should be able to try to apply it. It's a pretty weak statement, but it's something that you should check. It's definitely pretty much a necessary condition for dynamic programming to make sense. And so optimal substructure here means that if I take some shortest path and I look at a subpath of that shortest path, I claim that it too is a shortest path. Okay, with its respective endpoints. Obviously not between the same endpoints, but if I have some shortest path between two endpoints, I take any subpath, that's also a shortest path. This is one version of optimal substructure. This one turns out to be true for this setup. And how should I prove an optimal substructure property? Cut and paste. Yep, that works here too. I mean, this isn't always true, but it's a good technique here. So we're going to think about, and I'll do essentially a proof by picture here. So suppose you have some subpath of some shortest path. So let's say the subpath is x to y, and the path goes from u to v. So we assume that uv is the shortest path. We want to prove that xy is the shortest path. Well, suppose xy isn't the shortest path. Then there's some shorter path that goes from x to y. But if you have some shorter path from x to y than this one, then I should just erase this part of the shortest path from u to v and replace it with this shorter one. So if this is some hypothetical shorter path. So suppose this existed. If that existed, then I should just cut the old path from x to y and paste in this new one from x to y. It's strictly shorter, therefore I get a strictly shorter path from u to v, but I assume u to v was the shortest path contradiction. Okay, so there is no shorter path, and that proves the lemma. That we have this subpaths of shortest paths are shortest paths. Okay, this should now be a pretty familiar proof technique, but there's yet another instance of cut and paste. Okay, so that's a good sign for computing shortest paths. I mean, in terms of dynamic programming, we won't look directly at dynamic programming here because we're going to aim for greedy, which is even stronger. But next Monday, we'll see some dynamic programming approaches. Intuitively, there are some pretty natural subproblems here. I mean, going from u to v, if I want to find what's the shortest path from u to v, well, that's a particular problem. Maybe it involves computing shortest paths from u to some intermediate point x and then from x to u, something like that. That feels good. That's like quadratically many subproblems and v squared subproblems. Sounds like that would lead to a dynamic program. You can make it work out. It's just a little bit trickier than that. And we'll see that next Monday. So, but thinking about this intermediate point, we get something called the triangle inequality. So you've probably heard some form of the triangle inequality before. It holds in all sorts of geometric spaces, but it also holds for shortest paths, which is slightly less obvious. Or more obvious, I guess, depending on your inclination. So if you have any triple of vertices, the shortest path from u to v is at most the shortest path from u to x plus the shortest path from x to v. Of course, here I mean shortest path weight from u to x and the shortest path weight from x to v. So this should be pretty natural just from the statement. It's even more natural if you draw the picture. So we have some vertex u. I'm using wiggly lines to denote potentially long paths as opposed to edges. We have some intermediate point x, and we have some target v. And we're considering these three shortest paths. This is the shortest path from u to v, or this is its weight. This is the shortest path from u to x, and here's its weight. And the shortest path from x to v, and here's its weight. And the point is, well, this should be the shortest path, or a shortest path from u to v. And in particular, one such path is you go from u to x, and then you go from x to v. So, I mean, this sum is just measuring the length of this particular path. Take shortest path here, take shortest path here. And this is supposed to be the min over all paths. So certainly this is at most this particular path, the sum of these two values. Okay, another proof by picture. Clear? Okay, this stuff is easy. Soon we'll get into some more exciting algorithms. Well, we'll get into algorithms in particular, which is always more exciting. Today we're going to look at a particular version of shortest paths called, or the shortest paths problem, called the single source shortest path problem. Okay, it's a little bit more general from go from A to B. The problem is you're given a source vertex, and you want to know how to get from that source vertex to everywhere else. So we'll call the source vertex S, and from that source we want to find, let's say, the shortest path weights from S to everyone. In particular, we'd also like to know the shortest paths, but that isn't too much harder. So that's delta of S comma V for all vertices V. Okay, so this is actually a little bit harder than the problem we started with of getting from Alderaan to Cambridge. Now we want to get from Alderaan to the entire universe. Okay, it turns out, this is sort of one of the weird things about shortest paths. According to the state of the art we know today, which seems to be, well, it seems like the following statement will remain true for all time, but we don't know. The best algorithm for solving the A to B problem, given S, given T, go from S to T, is no easier than this problem. So the best ways we know how to solve going from A to B is to solve how to go from A to everywhere else. So we sort of can't help ourselves but to solve this problem, turns out. Today we're going to look at a further restriction on this problem because this is a bit tricky. We'll solve it next class. But today we're going to get rid of the negative weight cycle issue by forbidding negative weights. So we're going to assume that all of the edge weights are non-negative, so for all vertices U and V. So in particular, shortest paths exist, provided paths exist. And we don't have to worry about these minus infinities. Delta of UV is always bigger than minus infinity. Still might be plus infinity if there's no path, but this will make life a lot easier. And the algorithm we'll cover today really requires this property. You can't get away without it. Next class we'll get away without it, with a fancier and slower algorithm. So, as I've hinted at, the main idea we're going to use for the algorithm today is greedy, which should be faster than dynamic programming generally. And the tricky part will be proving that the greedy algorithm actually works. So I think there's pretty much only one natural way to go about, well, there's one way that works, go about greedy, let's say. It's maybe not the obvious one. So let me give you a little bit of setup. The invariant we're going to maintain is that at all times we have estimates on the distances from the source to every vertex. When I say distance, I mean shortest path weight. I'm going to use weight and distance interchangeably here for more intuition. And in particular, I want to maintain the set of vertices where those estimates are actually the right answer. This is little s, this is big S. So the big S will be the set of all the vertices where I know the answer. What is the shortest path distance from little s to that vertex in big S? So for starters, which distance do I know?
Big.
Sorry? S. Yeah, I know the shortest path distance from S to S because if I assume that all of my weights are non-negative, I really can't get from S to S any faster than not doing anything. Okay, if I have a negative weight cycle, maybe distance from S to S is minus infinity. Okay, but I can't have negative weights, so there's no way I can get from S to S in any faster than 0 time. There might be a longer path that still has 0 cost, but it can't be any better than 0. So in particular, I know that. So initially, S is certainly an S. Okay, and the idea is we're going to accumulate more and more vertices that we know. So at some point we know the distances from some of the vertices. So we have this, we have some cloud here. This is S, and this is everything else. This is the graph G. This is a subset of the vertices. And there's some edges that go out from there. And so we have estimates on how to get to these vertices. Some of them we may not have even seen yet. They may not be connected to this portion of S. I mean, not directly. They might be connected by some longer path. They might be in a completely different connected component. We don't know yet. Some of them we have estimates for because we've sort of seen how to get there from S. And the idea is, among all of these nodes where we have estimates and how to get from little s, which is some vertex in here, to these vertices, we're going to take the one for which the estimate is smallest. That's the greedy choice. And we're just going to add that vertex to S. So S grows one vertex per step. For each step, we're going to add to S the vertex. Of course, again, this is not a unique, it's a vertex. V in V minus S, so something we haven't yet computed. Whose estimated distance from S is minimum. So we look at all the vertices we haven't yet added to S. Just take the one where we have the estimated smallest distance. The intuition is that that should be a good choice. Because if I pick the one that's closest to S, closest to little s, among all the ones that I've seen, among all the paths that I've seen, I sort of have to buy into that those are good paths. But I mean, maybe there's some path I didn't see. Maybe you go out to here, and then you take some other path to some vertex which we've already seen. Okay, the worry is, well, I better not say that that's the shortest path because there may have been some other way to get there. Right? As soon as I add something to S, I declare I've solved the problem for that vertex. I can't change my answer later. Okay, the estimates can change until they get added to S. So I don't want to add this vertex to S because I haven't considered this path. Well, if all my weights are non-negative, and I take the vertex here that has the shortest estimate from S, then so let's suppose this one is the shortest one. Then this can't be a shorter path because the distance estimate, at least from S to that vertex, is larger than from S to that vertex. So no way could I make the path longer and decrease the distance. That's the intuition. Okay, it's a little bit fuzzy here because I don't have any induction hypotheses set up, and it's going to be a lot more work to prove that, but that's the intuition why this is the right thing to do. Okay, you have to prove something about the distance estimates for that to be a proof, but intuitively it feels good. Always a good starting point. Okay, and then presumably we have to maintain these distance estimates. So the heart of the algorithm is updating distance estimates. I mean, choosing the best vertex to add to S, that's one step. Then updating the distance estimates is sort of where the work is. And it turns out we'll only need to update distance estimates of some of the vertices, the ones that are adjacent to V. V was the vertex we just added to S. So once we add somebody to S, so we grow S by a little bit, then we look at all the new edges that go out of S from that vertex, we update something. Okay, that's the idea. So that's the idea for how we're going to use greedy. Now I'll give you the algorithm. So this is called Dijkstra's algorithm. Dijkstra is a famous recently late, if that makes sense, recently late computer scientist from the Netherlands. And this is probably the algorithm he's most famous for. So the beginning of the algorithm is just some initialization, not too exciting. Okay, but let me tell you what some of the variables mean. So this D is some array indexed by vertices, and the idea is that D of x is the distance estimate for x, so from S to x. So in particular, it's going to equal the real shortest path weight from S to x when we've added x to our set capital S. Okay, so this is in particular going to be the output to the algorithm. Do you have a question or stretching? Good. So d of x, when we're done, d of x is the output. For every vertex, it's going to give us the shortest path weight from S to that vertex. Along the way, it's going to be some estimated distance from S to that vertex, and we're going to improve it over time. This is an infinity. So initially, we know that the distance, the distance from S to S is 0, so we're going to set that to be our estimate. It's going to be accurate. Everything else, we're just going to set to infinity because we may not be connected. From the beginning, we don't know much. S initially is going to be infinity. Immediately, we're going to add little s to big S. And then the interesting part here is Q, which is going to consist of initially all the vertices in the graph. And it's going to not just be a Q, as the letter suggests. It's going to be a priority Q. So it's going to maintain, in particular, the vertex that has the smallest distance estimate. So this is a priority Q. This is really an abusive notation for a data structure. Okay, so this could be a heap or whatever. The vertices are keyed on D, our distance estimate. So in particular, S will have this is going to be a min heap. S will be the guy who has the minimum. Everyone else has the same key initially. And we're going to repeatedly extract the minimum element from this queue and do other things. Okay, so this is initialization. Okay, I'm going to call that initialization because it's a pretty simple thing. It just takes linear time, nothing fancy going on. The heart of the algorithm is all in 6 lines. And so we're sort of, this is not really a step. The first step here that we need to do is we take the vertex whose distance estimate is minimum, so that among all the vertices not yet in S, currently S is empty, Q has everyone. In general, Q will have everyone except S. So we'll take the vertex U that has the minimum key in that priority queue. So extract the min from Q. Okay. We're going to add little u to S, claim that that is now, I mean, that's exactly what we're saying here. We add to S that vertex that has minimum distance estimate. And now we need to update the distances. So we're going to look at each adjacent vertex for each V in the adjacency list for U. We look at a few distances. So that's the algorithm, more or less. This is the key. I should define a little bit what's going on here. We talked mainly about undirected graphs last time. Here we're thinking about directed graphs, and the adjacency list for U here is just going to mean give me all the vertices for which there is an edge from U to V. So this is the outgoing adjacency list, not the incoming adjacency list. Undirected graphs, you list everything. Directed graphs, here we're only going to care about those ones. So for every edge UV, is what this is saying, we're going to compare the current estimate for V and this candidate estimate, which intuitively means you go from S to U, that's D of U, because we now know that that's the right answer. This in fact equals, we hope, assuming the algorithm is correct, this should be the shortest path weight from S to U, because we just added U to S. And whenever we add something to S, it should have the right value. So this is we could say, well, you take the shortest path from S to U, and then you follow this edge from U to V. That has weight W of UV. That's one possible path from S to V. And if that's a shorter path than the one we currently have in our estimate, if this is smaller than that, then we should update the estimate to be that sum, because that's a better path. So add it to our database of paths, so to speak. A very intuitive operation. Clearly should not do anything bad. I mean, these should be paths that make sense. We'll prove that in a moment. That's the first part of correctness, that this never screws up. And then the tricky part is to show that it finds all the paths we care about. This step is called a relaxation step. Relaxation is always a difficult technique to teach to MIT students. It doesn't come very naturally, but okay, it's a very simple operation. It comes from optimization terminology, programming terminology, so to speak. And can anyone tell me, does this inequality look familiar at all? Look kind of, especially when you start writing it this way. If you say, well, the shortest path from S to V and the shortest path from S to U and some edge from U to V. Does that look like anything we've seen? In fact, it was on this board, but I just erased it. Triangle inequality, yeah. So this is trying to make the triangle inequality true. Certainly, the shortest path from S to V should be less than or equal to, not this, not greater than, the shortest path from S to U plus some, whatever path from U to V. This shortest path should be at most that. So this is sort of a somewhat more general triangle inequality. And we want to, certainly it should be true. So if it's not true, we fix it. If it's greater than, we make it equal. We don't want to make it less than, because that's not always true. Okay, but certainly it should be less than or equal to. So this is fixing the triangle inequality. It's trying to make that constraint more true. And an optimization that's called relaxing the constraint. Okay, Okay, so we're sort of relaxing the triangle inequality here. Over and over and over. And by the end, we should have all the shortest paths. That's the claim. So very simple algorithm. Let's try it out on a graph. And that should make it more intuitive why it's working. And then the rest of the lecture will be proving that it works. Yeah, this is enough room. So let's take, I should mention one other thing here, sorry. That whenever we change d of v, this is changing the key of v in the priority queue. So implicitly what's happening here in this assignment, it's getting a bit messy, is a decrease key operation. Okay, which we talked briefly about last class in the context of minimum spanning trees, where we're also decreasing the key. The point is we're changing the key of one element in this relaxation step in the priority queue so that, if it now becomes the minimum, we should extract it here. And we're only ever decreasing keys because we're always replacing larger values with smaller values. So we'll come back to that later when we analyze the running time. But there is some data structure work going on here. Again, we're abusing notation a bit. OK, so here's a graph with edge weights. Okay, and I want my priority queue over here. And I'm also going to draw my estimates. Okay, now I don't want to cheat. So we're going to run the algorithm on this graph. S will be A. And I want to know the shortest path from A to everyone else. So you can check, okay, paths exist. So hopefully everything should end up a finite value by the end. All the weights are non-negative. So this algorithm should work. The algorithm doesn't even need connectivity, but it does need that all the weights are non-negative. So we run the algorithm. For the initialization, we set the distance estimate for our source to be 0, because in fact there's only one path from A to A, and that's to do nothing, the empty path. So I'm going to put a key of 0 over here. And for everyone else, we're just going to put infinity, because we don't know any better at this point. So I'll put keys of infinity for everyone else. Okay, so now you can see, what the algorithm does is extract the minimum from this queue. And given our setup, we'll definitely choose S, or in this case A. Because it has a weight of 0, everyone else has a quite a bit larger weight. Okay, so we look at S. I'll use A here. So we look at A, we add A to our set S, so I'm going to square something when it's now removed from the queue. It will never go back in, because we never add anything to the queue. Start with all the vertices and extract and decrease keys, but we never insert. So A is gone. Okay, and now I want to update the keys of all of the other vertices, and the claim is I only need to look at the vertices that have edges from A. So there's an edge from A to B, and that has weight 10. And so I compare, well, is it a good idea to go from A to A, which costs nothing, and then to go along this edge AB, which costs 10? Well, it seems like a pretty good idea, because that has a total weight of 0 plus 10, which is 10, which is much smaller than infinity. So I'm going to erase this infinity, write 10. And over in the queue as well. That's the decrease key operation. So now I know a path from A to B. Good. A to C is the only other edge. 0 plus 3 is less than infinity. So cool. I'll put 3 here for C. And C is there. Okay. The other vertices I don't touch. I'm going to rewrite them here, but the algorithm doesn't have to copy them. Those keys were already there. It's just touching these two. OK, that was pretty boring. Now we look at our queue, and we extract the minimum element. So A is no longer in there, so the minimum key here is 3. So the claim is that this is the shortest path from A to C here is the shortest path from A to C. There's no other shorter way. You can check that, and we'll prove it in a moment. Cool, so we remove C from the list. It's gone. And then we look at all of the outgoing edges from C. So there's one that goes up to B, which has weight 4. 4 plus 3, which is the shortest path weight from A to C. So going from A to C, then C to B, should cost 3 plus 4, which is 7, which is less than 10. So we found an even better path to get to B. It's better to go like this than it is to go like that. So we write 7 for B. And there's an outgoing edge from C to D, which costs 8. 3 plus 8 is 11. 11 is less than infinity, last I checked. So we write 11 for D. Then we look at E. We have 3 plus 2 is 5, which is less than infinity. So we write 5 for the new key for E. At this point, we have finite shortest paths to everywhere. But they may not be the best ones. So we have to keep looking. Okay, we just, next round of the algorithm, we extract the minimum key among all these. Okay, it's not B, which we've seen and probably know the answer to, but it's E. E has the smallest key. So we take this, we now declare this to be a shortest path. The way we got to E was along this path, A to C, C to E. Declare that to be shortest. We claim we're done with E, but we still have to update what about all the outgoing edges from E. There's only one here. It costs 5 plus 9, which is 14, which is bigger than 11. So no go. That's not an interesting path. Our previous path, which went like this at a cost 11, is better than the one we're considering now. I'm drawing the whole path, but the algorithm is only adding these two numbers. Okay, good. So I don't change anything. 7, 11. And 5 is removed, or E is removed. Our new keys are 7 and 11. So we take the key 7 here, which is for element B, for text B. We declare the path we currently have in our hands from A to B, which happens to be this one. Algorithm can't actually tell this, by the way, but we're drawing it anyway. This path A, C, B is their candidate shortest path. Claim is that it is indeed shortest. Now we look at all the outgoing edges. There's one that goes back to C at a cost of 7 plus 1, which is 8, which is bigger than 3, which is good. Better, we already declared C to be done. But the algorithm checks this path and says, oh, that's no better. And then we look at this other edge from B to D. That costs 7 plus 2, which is 9, which is better than 11. So we, in fact, found an even shorter path. So the shortest path weight now for D is 9, because there's this path that goes A, C, B, D, for a total cost of 3 plus 4 plus 2 is 9. Cool. Now there's only one element in the queue. We remove it. D, we look at the outgoing edges. There's one going here, which costs 9 plus 7, which is 16, which is way bigger than 5. So we're done. Don't do anything. At this point, the queue is empty. And the claim is that all these numbers that are written here, the final values, are the shortest path weights. Okay, this looks an awful lot like a 5, but it's an S. It has a weight of 0. Okay? I've also drawn in here all the shortest paths. And this is not hard to do. We're not going to talk about it too much in this class, but it's mentioned a little bit more detail in the textbook. It's something called the shortest path tree. It's just something good to know about if you actually want to compute shortest paths. In this class, we mainly worry about the weights because it's pretty much the same problem. The shortest path tree is the union of all shortest paths. And in particular, if you look at each vertex in your graph and you consider the last edge into that vertex that was relaxed among all vertices U, you look at the edges UV, say, was that the last one relaxed? So just look at the last edges we relaxed here. You put them all together. That's called the shortest path tree. And it has the property that from S to everywhere else, there's a unique path down the tree. And it's the shortest path. It's the shortest path that we found. Okay, so you actually get shortest paths out of this algorithm, even though it's not explicitly described. All we're mainly talking about are the shortest path weights. Algorithm clear at this point? Feels like it's doing the right thing. You can check all those numbers are the best paths. And now we're going to prove that. So, correctness. So the first thing I want to prove is that relaxation never makes a mistake. If it ever sets d of v to be something, I want to prove that d of v is always an upper bound on delta. So we have this invariant, d of v is greater than or equal to delta of s comma v for all v. And this invariant holds at all times. So after initialization, it doesn't hold before initialization because d isn't defined then. But if you do this initialization where you set s to 0 and everyone else to infinity, and you take any sequence of relaxation steps, then this invariant will hold after each relaxation step you apply. This is actually a very general lemma. It's also pretty easy to prove. It holds not only for Dijkstra's algorithm, but for a lot of other algorithms we'll see. That use pretty much every algorithm we see will involve relaxation. And this is saying no matter what relaxations you do, you always have a reasonable estimate in the sense it's less than or equal to, or it's greater than or equal to the true shortest pathway. So it should be converging from above. So that's the lemma. Let's prove it. Any suggestions on how we should prove this lemma? What technique might we use? What's that? Cut and paste would be good for optimal substructure. Cut and paste maybe sort of what's going on here, but not exactly. Something a little more general. Just intuition here. It doesn't have to be the right answer. In fact, many answers are correct. Have plausible proofs. Induction. Yeah. So I'm not going to write induction here, but it's effectively we're using induction. That's the answer I was expecting. So there's sort of an induction already in time going on here. We say after initialization this should be true. That's our base case. And then every relaxation we do, it should still be true. So we're going to assume by induction that all the previous relaxations worked. And then we're going to prove that the last relaxation, whatever it is, works. So first let's do the base case. So this is after initialization. So say initially. So initially we have d of s equal to 0. And we have d of v equal to infinity for all other vertices, for all vertices v not equal to s, little s. Okay? Now we have to check that this inequality holds. Well, we have delta of s comma s. We've already argued that that's 0, because you can't get negative when there are only non-negative edge weights. So that's the best. So certainly 0 is greater than or equal to 0. And we have everything else. Well, I mean, delta of s comma v is certainly less than or equal to infinity. So this holds. Everything is less than or equal to infinity. So base case is done. So now we do an induction. And I'm going to write it as a proof by contradiction. So let's say, suppose that this fails to hold at some point. So suppose, for contradiction, that the invariant is violated. So we'd like to sue the violator and find a contradiction. So it's going to be violated. So let's look at the first violation, the first time it's violated. So this is essentially, again, a proof by induction. So let's say we have some violation d of v is less than delta of s comma v. That would be bad if we somehow got an estimate smaller than the shortest path. Well, and the nice thing about looking at the first violation is we know sort of by induction that all previous, all other values are correct. Okay, d of v is the first one where we screwed up. So the invariant holds everywhere else. Well, what caused this to fail, this invariant to be violated, is some relaxation, okay, on d of v. So we had some d of v, and we replaced it with some other d of u plus the weight of the edge from u to v. And somehow this made it invalid. Okay, so d of v is now somehow less than this. We just set d of v to this. So this must be less than delta of s comma v. Claim is that that's not possible because, so let me rewrite a little bit. We have d of u plus w of uv. And we have our induction hypothesis, which holds on u. U is some other vertex. We know that d of u is at least delta of s comma u. So this has to be at least delta of s comma u plus w of u comma v. Now, what about this w of u comma v? Well, that's some path from u to v. Okay, so it's got to be bigger than the shortest path, or equal. So certainly this is greater than or equal to delta of u comma v. Okay, it could be larger if there's some multi-edge path that has smaller total weight. But it's certainly no smaller than delta of u comma v. And this looks like a good summation. Delta of s to u and u to v is triangle inequality. Yeah. So it's upside down here, but the triangle is s to u, u to v. So this is only longer than s to v. Okay, so we have this thing which is simultaneously greater than or equal to the shortest path weight from s to v, and also strictly less than the shortest path weight from s to v. So that's a contradiction. And maybe contradiction isn't the most intuitive way to proceed. The intuition here is whenever you assign d of v, you have a path in mind. You inductively had a path from s to u, then you added this edge. So that was a real path. It should be we always know that every path has weight greater or equal to the shortest path. So it should be true. And here's the inductive proof. All right. Moving right along. So this was an easy warm-up. We have greater than or equal to. Now we have to prove less than or equal to at the end of the algorithm. This is true all the time. Less than or equal to will only be true at the end. So we're not going to prove less than or equal to quite yet. I'm going to prove another lemma, which again, so both of these lemmas are useful for other algorithms too. So we're sort of building some shortest path theory that we can apply later. This one will give you some intuition about why relaxation, not only is it not bad, but it's actually good. Not only does it not screw up anything, but it also makes progress in the following sense. So suppose you knew the shortest path from S to some vertex. Okay, so you go from S to some other vertices, then you go to U, then you go to V. Suppose that is a shortest path from S to V. Okay, and also suppose that we already know in D of U the shortest path weight from S to U. So suppose we have this equality. We now know that we always have a greater than or equal to. Suppose they're equal for U. Okay, the vertex just before V in the shortest path. Okay, and suppose we relax that edge, UV. Okay, which is exactly this step. This is relaxing the edge UV, though I didn't just call it relaxation here. Then after that relaxation, d of v equals delta of SV. So if we had the correct answer for u and we relax uv, then we get the correct answer for v. Okay, this is good news. It means if inductively somehow we can get the right answer for u, now we know how to get the right answer for v. Okay, now in the algorithm we don't actually know what the vertex just before v in the shortest path is, but in the analysis we can pretty much know that. So we have to prove this lemma. This is actually even easier than the previous one. Don't even need induction. This is just, you work through what's going on in relaxation and it's true. So here we go. So we're interested in this value, delta of s comma v. And we know what the shortest path is. So the shortest path weight is the weight of this path. Okay, so we can write down some equality here. Well, I'm going to split out the first part of the path and the last part of the path. So we have, I'll say, the weight from s, so this part of the path from s to u, plus the weight of this edge, u comma v. Remember, we could write w of a path, and that was the total weight of all those edges. So what is this? The weight of this path from s to u. Or what property should I use to figure out what that value is? Yeah?
Well, we said it was the shortest path, right? So it has to be the optimal subpath.
S to v is the shortest path, right? So by optimal substructure, from s to u is also a shortest path. So this is delta of su. Cool. Okay. We'll hold on for now. That's all we're going to say. On the other hand, we know from this lemma that no matter what we do, d of v is greater than or equal to delta of s comma v. So let's write that down. So there's a few cases, and this will eliminate some of the cases. By that lemma correctness 1, we know that d of v is greater than or equal to delta of s comma v. So it's either equal or greater than at all times. So I'm thinking about the time before we do the relaxation, this uv. So at that point, this is certainly true. So either they're equal before relaxation, or it's greater. Okay, if they're equal before relaxation, we're happy, because relaxation only decreases values by correctness 1. It can't get any smaller than this, so after relaxation it will also be equal. Okay, so in this case we're done. So that's a trivial case. So let's now suppose that d of v is greater than delta of s comma v before relaxation. That's perfectly valid. Hopefully now we fix it. Okay, well the point is, we know this delta of s comma v. It is this sum. So it's also, okay, we also know this. Okay, so we plug these, so delta of s comma u we know is d of u. And we have this w of u comma v. So delta of sv is d of u plus w of uv. Because we're assuming we have this shortest path structure where you go from s to u, and then you follow the edge uv. So we know this. So we know d of v is greater than d of u plus w of uv. By golly, that's this condition in relaxation. So just checking, relaxation actually does something here. Okay, if you had the wrong distance estimate, this if condition is satisfied. Therefore, we do this. So in this case, we relax. So just relax. Okay, and then we set d of v to d of u plus w of uv, which is what we want. Okay, so we set d of v to d of u plus w of uv. And this equals, as we said here, delta of s comma v, which is what we wanted to prove. Done. Okay, I'm getting more and more excited as we get into the meat of this proof. Any questions so far? Good. Now comes the hard part. Okay, these are both very easy lemmas, right? Okay. Yeah. Let's, I'll use these two boards. We don't need these proofs anymore. We just need these statements. Correctness 1, correctness lemma. Great names. So, now finally we get to correctness 2. So we had 1 and 1.5. So I guess correctness is itself a mini trilogy, the mini series. Okay. So correctness 2 says when the algorithm is done, we have the right answer. This is really correctness, but it's going to build on correctness 1 and correctness lemma. So we want d of v to equal delta of s comma v for all vertices v at the end of the algorithm. That is clearly our goal. Now, this theorem is assuming that all the weights are non-negative, just to repeat. It doesn't assume anything else. So it's going to get the infinities right, but if there are minus infinities, all bets are off. Okay, even if there's any negative weight edge anywhere, it's not going to do the right thing, necessarily. Okay, but assuming all the weights are non-negative, which is reasonable if they're measuring time or usually money. Usually it costs money to travel along edges, they don't pay you to do it. But who knows? All right. So I need just to say a few things. One of the things we mentioned somewhere along the way is when you add a vertex to S, you never change its weight. Okay, that actually requires some proof. I'm just going to state it here. It's not hard to see. D of v doesn't change. Okay, this is essentially an induction. Once v is added to S. Okay, this will actually follow by something we'll say in a moment. Okay, so all I really care about is when a vertex is added to S, we better have the right estimate, because after that, we're not going to change it, let's say. Okay, we could define the algorithm that way. We're not, but we could. Okay, I'll say more about this in a second. So all we care about is whether d of v equals delta of s comma v. That's what we want to prove. So it's clearly that should be true at the end. But it suffices to prove that it holds when v is added to s, to capital S. Okay? This actually implies the first statement. It's sort of a funny implication. But if we can prove this, that d of v equals delta of s comma v when you add to s, well, we know relaxation only decreases values, so it can't get any smaller from correctness 1. Correctness 1 says we can't get any smaller than delta. So if we get equality at that point, we'll have equality from then on. So that actually implies d of v never changes after that point. Okay, so we're going to prove this. Good. Well, suppose it isn't true. So this will be proof by contradiction. Suppose for contradiction that this fails to hold, and let's look at the first failure. Suppose U is the first vertex that's about to be added to S. I want to consider the time right before it's added to S. For which we don't have what we want. These are not equal. The d of u does not equal delta of s comma u. Well, if they're not equal, we know from correctness 1 that d of v is strictly greater than delta of s comma u. So d of u. So we have d of u strictly greater than delta of s comma u. And that's the beginning of the proof. Nothing too exciting yet. Just some warm-up. Okay, but this, we've used already correctness 1. I think that's the only time that we use it in this proof. Okay, so I sort of just want to draw a picture of what's going on, but I need a little bit of description. So let's look at the shortest path, right? Somehow d of u is greater than the shortest path. So consider the shortest path, or a shortest path. Let p be a shortest path. Not just any shortest path, but the shortest path from S to U. Okay, so that means that the weight of this path is the shortest path weight, so we have some equations for what's going on here. So we care about delta of SU. Here's a path with that weight. It's got to be 1, because shortest paths exist here. Slight exceptional cases if it's a plus infinity, but I'm not going to worry about that. So let me draw a picture somewhere. So we have S, we have U. Here is the shortest path from S to U. That's P. No idea what it looks like so far. Now, what we also have is this notion of capital S. So I'm going to draw capital S. So this is big S. We know that little s is in big S. We know that U is not yet in big S. So haven't screwed up anything yet, right? This path starts in S and leaves it at some point, because until we're about to add U to S, so it hasn't happened yet. So U is not in S. Fine. What I want to do is look at the first place here where the path P exits S. So there's some vertex here, let's call it X. There's some vertex here, call it Y. Okay? Possibly X equals S, possibly Y equals U. But it's got to exit somewhere, because it starts inside and it ends up outside, and it's a finite path. Okay, so consider the first time it happens, not the second time, first. Okay, so consider first edge, XY, where P exits capital S. The shortest path from S to U exits capital S. It's got to happen somewhere. Cool. Now, what do we know? Little x is in S. So it has the right answer. Because U, we were about to add U to S, and that was the first violation of something in S that has the wrong D of U, or D of X estimate. So D of X equals delta of S comma X. Because we were looking at the first violation, X is something that got added before. So by induction on time, because we had the first violation, D of X equals the shortest path weight from S to X. So that's good news. Now we're trying to apply this lemma. It's the only thing left to do. We haven't used this lemma for anything. So we have this setup. If we already know that one of the D values is the right answer, and we relax the edge that goes out from it, then we get another right answer. So that's what I want to argue over here. We know that the D of X equals this weight, because again, shortest subpaths are shortest paths are shortest paths. We have optimal substructure. So this is the shortest path from S to X. Might not be the only one, but it is one. So we know that matches. Now, I want to think about relaxing this edge XY. Well, X is in capital S. And the algorithm says whenever you add a vertex u to the big set S, you relax all the edges that go out from there. Okay, so when we added x to S, and we're now like far in the future, we're about to add some other vertex. Right after we added x to S, we relaxed this edge xy because we relaxed every edge that goes out from x. Okay, whatever they were. Some of them went into S, some of them went out. Here's one of them. So when we added x to S, we got excess. Added x to S, we relaxed the edge xy. Okay, so now we're going to use the lemma. So by the correctness lemma, what do we get? Well, we had this correct shortest pathway to x now. We relaxed the edge xy. So now we should have the correct shortest pathway for y. D of y equals delta of sy. Okay, this is sometime in the past. In particular, now it should still be true. Because once you get down to the right answer, you never change it. Okay, we should be done. Okay, why are we done? Well, what else do we know here? We assume something for contradiction, so we better contradict that. We assume somehow d of u is strictly greater than delta of su. So d of u here is strictly greater than the length of this whole path. Well, we don't really know whether u equals y. It could not. But what do we know about this shortest path from S to y? Well, it could only be shorter than from S to u, because it's a subpath, and it's the shortest path because it's a subpath of a shortest path. The shortest path from S to u S to y has to be less than or equal to the shortest path from S to u. Okay, S to y less than or equal to S u. Okay, just because it's a subpath. Well, now okay, I'm closer. I've got delta of s comma u now. Somehow I want to involve d of u. So I want to relate d of y to d of u. What do I know about d of u? Yeah.
It's bigger because we have a min heap.
It's d of u is smaller
Right.
because we have a min heap. Yeah. We always chose u. It's way down here. We chose u, this is the middle of the algorithm. There's a reason I kept this, to be the minimum key. This is keyed on d. So we know that at this moment when we're trying to add u to S, right, y is not in S and u is not in S. They might actually be the same vertex, but both of these vertices, whether same or not, are outside S. We chose d of u. We chose u because d of u has the smallest d estimate. So y, d of y, has to be greater than or equal to d of u. It might be equal if they're the same vertex, but it's got to be greater than or equal to. So d of y here is greater than or equal to d of u. Just now. So here we're using the fact that we actually made a greedy choice. It's the one place we're using the greedy choice. Better use it somewhere, because you can't just take an arbitrary vertex and declare it to be done. Got to take the greedy one. Okay, now we have d of u is less than or equal to delta of su, which contradicts this. Okay, sort of magical that all just worked out, but sort of like the previous proofs, you just see what happened, and it works. Okay, that's the approximation. The only real idea here is to look at this edge. Look, in fact, you could look at this edge too, but let's look at some edge that comes from S and goes out of S, and argue that, well, x has to be correct, and when we made x correct, y had to be correct. And now, well, why the hell were you looking at u? Y is the thing you should have looked at, and there you get a contradiction, because y had the right answer. If u equals y, that's fine, or if u and y were sort of equally good, that's also fine, if all these weights were 0. So the picture might actually look like this. But in that case, D of U was the correct answer. It was delta SU. We assumed that it wasn't. That's where we're getting a contradiction. Pretty clear? Okay, go over this proof. It's a bit complicated, naturally. Okay, we have a little bit more to cover. Some easier stuff. Okay, the first thing is what's the running time of this algorithm? I'll do this very quick because we've actually seen this running time before in last class. There was some initialization. The initialization, which is no longer here, is linear time. No big deal. Okay, extract min. Well, that's some data structure. So we have something like size of v. Every vertex we extract the min once, and that's it. So they're size of v, extract mins. Okay, so that's pretty simple. Okay, then we had this main loop. I mean, this is a completely conceptual operation. S is not actually used in the algorithm. It's just for thinking. Okay, so this takes 0 time. Gotta love it. Okay, and now the heart is here. So how many times does this loop iterate? That's the degree of U. So what is the total number of times that we execute a relaxation step? Doesn't necessarily mean we do this, but we at least execute this body. Over the whole algorithm, how many times do we do this? For every vertex, we look at all the outgoing edges from there. So the total would be number of edges, yeah. So this is number of edges iterations. Okay, this is essentially the handshaking lemma we saw last time, but for directed graphs. And we're only looking at the outgoing edges. So there's not a factor of 2 here, because you're only outgoing from one side. So we have number of iterations. In the worst case, we do a decrease key for every one. So at most, E decrease keys. Okay, so the time is, well, we have V extract mins, so the time to do an extract min, whatever that is. And we have E decrease keys, whatever that is. And this is exactly the running time we had for Prim's algorithm for minimum spanning tree last time. And it depends what data structure you use, what running time you get. Yeah. So I'm going to skip the whole table here. But if you use an array, the final running time will be v squared, because you have order v extract min, and you have constant time decrease key. If you use a binary heap, which we know and love, then we have order log v for each operation. And so this is v plus e log v. And so that's what we know how to do. And if you use this fancy data structure called a Fibonacci heap, you get constant time decrease key amortized. And you get an e plus v log v, worst case bound on the running time. So this is the best. This is the best we know how to solve shortest paths without any extra assumptions. Single source shortest paths with non-negative edge weights in general. Okay, this is almost as good, and this is sometimes better than that, but these are essentially irrelevant, except that you know how to do these. You don't know how to do a Fibonacci heap unless you read that chapter of the book. That's why we mentioned the top 2 running times. Okay, I want to talk briefly about a simpler case, which you may have seen before, and so it's sort of fun to connect this up to breadth first search in a graph. So, I mean, that ends Dijkstra, so to speak. But now I want to think about a special case where the graph is unweighted, meaning W of uv equals 1 for all vertices u and v. Okay, suppose we had that property. Can we do any better than Dijkstra? Can we do better than this running time? Well, we probably have to look at all the edges and all the vertices, so the only thing I'm questioning is this log v. Can I avoid that? I gave away the answer a little bit. The answer is called breadth first search, or BFS, which you have probably seen before. It's one of the, next to depth first search, it's one of the standard ways to look at a graph. But we can say a little bit more than you may have seen before. Breadth first search is actually Dijkstra's algorithm. Kind of nifty. There are two changes. The first change is that breadth first search does not use a priority queue. I'll just tell you what it uses instead. You can use a queue, a first in, first out, honest to goodness queue, instead of a priority queue. Okay, turns out that works. Instead of doing extract min, you just take the first thing off the queue. Instead of doing decrease key, okay, here's a subtlety, but this if statement changes a little bit. So here's the relaxation step. So in order to relax, you say this much simpler thing. If we haven't visited v yet, then we declare it to have the shortest path weight. Say d of v is d of u plus 1, which is the weight of the edge uv, and we add u v to the queue. Add it to the end of the queue. So this is now, we start with the queue empty. Actually, it will just contain the vertex s, because that's the only thing we know the shortest path for. So the queue is just for, I know the shortest path of this thing, just deal with it when you can. Look at all the outgoing edges when you can. So initially that's just s. You say, well, for all the outgoing edges, I mean, s has 0. All the outgoing edges from there have weight 1. Shortest path weight from the source is 1. Certainly can't do better than that if all the weights are 1. Okay, so we add all those vertices to the end of the queue. Then we process things in order, and we just keep incrementing their, if their value is d of u, add 1 to it, that's d of v. And then we're going to add v to s in the next, when we get to it in the queue. Okay, that is breadth first search, very simple. And you can look in the text for the algorithm and for an example, because I don't have time to cover that. But the key thing is that the time is faster. The time is order v plus e. Because, as before, we only look at each edge once. We look at all the outgoing edges from all the vertices. As soon as we set d of v to something, it will remain that. We never touch it. We're going to add it to s. That only happens once. So this if statement and so on, and the enqueuing is done order e times. Actually, e times, exactly. And enqueuing to a queue and dequeuing from a queue, that's what we use instead of extract min. Take constant time. It's the total running time. Number of vertices plus number of edges. Okay, not so obvious that this works, but you can prove that it works using the Dijkstra analysis. All you have to do is prove that the FIFO queue does exactly the same thing as a priority queue. Once you know that, by the correctness of Dijkstra, you get the correctness of breadth first search. So not only is breadth first search finding all the vertices, which is maybe what you normally use it for, but it finds the shortest path weights from S to every other vertex when the weights are all 1. So there we go. Introduction to shortest paths. Next time we'll deal with negative weights.